everyone, welcome to my class. Today I am covering Stokes Theorem. First, quick preview. Stokes Theorem is a higher dimensional version of Green's theorem. The Stokes Theorem relates the line integral of a vector field to a surface integral of the vector field. Let me first revisit the Green's theorem. The Green's theorem says the line integrals of vector field over a simple closed curve C equals to double integrals of partial derivative of q with respect to x minus partial derivative of q with respect to y over the region D enclosed by C, and the double integral is with respect to dA, equals to the double integrals of normal component of curl of vector field F over the region D. Now let's state the Stokes theorem. Let me scroll down. That's better. So the Stokes theorem says let S be a positive oriented surface given by z equals to function of gxy bounded by a simple closed curve C and capital F be a vector field. Then the line integrals of vector field F over the space curve C equals to the double integrals of curl F over the surface S. So that is the surface integrals of curl vectors curl F over the surface S. So now let me talk about the pictures here. The first diagram is for the Green's theorem. So in the first diagram, D is a region enclosed by the closed curve C. C is also right as del D, the boundary of D. And now let's go to the second diagram. In the second diagram, the Green's theorem is in the 2 dimensions down here. And then the Stokes theorem is the generalization of Green's theorem. So go to the space here. So here, this D is the region enclosed by the C in the 2 dimensions, and in the 3 dimension, as surface is the region bounded by this closed curve C, and Stokes theorem is here. Great. Let me make some point here. So, note number 1, if in special case, that's better, the surface is flat and lies in the xy plane with upward orientations, then our normal vector, the n we used in the Stokes theorem, is k. Then the surface integral becomes a double integral, and Stokes theorem becomes the Green's theorem. Awesome. Then note number 2, Stokes theorem can be used to compute either the line integrals or the surface integrals. Let me scroll you up. So here, either we use a Stokes theorem we use to compute either the line integrals, the left side compute the line integrals, or from the right side the surface integrals. Let me scroll down. Remember that to compute the line integral, curve C needs to be parameterized. Third, the orientation of the surface in its boundary should match. So that means in the orientation of the surface as well as the curve should match. So here is a counterclockwise, and the surface, counterclockwise curve is positive, and then the surface whose normal vector points upward is positive. Awesome. Let me scroll down. Now let's do some example. Evaluate the surface integrals of curl of vector field F over the surface S, where vector field is given as capital F equals to x squared sine g x xy, and S is the part of the paraboloid. Paraboloid is given z equals to 1 minus x squared minus y squared that lies above the xy plane oriented upward. Awesome. So let's move on. Let's start the solutions. So I think that's better. Here's better. Yeah. For the boundary curve, our paraboloid is z equals to 1 minus x square minus y square. So this is the paraboloid opening downward. Intersect the xy plane in the circle. So the cross sections of this paraboloid with the xy plane is x square plus y square equals to 1, this circle. Then it's easier for us to find the limit in the polar form. So let's write the parametric form of this circle. So x equals to cosine t, y equals to sine t, and obviously z is 0 and t between 0 and 2 pi. So our curve equation is rt equals to, that's the vector equation, rt equals to xt, yt, zt, cosine t, sine t, 0. So take its derivative, r prime t equals to cosine t, take the derivative cosine t, negative sine t, take the derivative sine t, cosine t, take the derivative 0, sine is 0. Also let's compute f of rt, the vector field. So f of rt equals to, what is our f? So our f is here. So x is square, put x equals to cosine t, put z equals 0, so sine 0, 0, everything is 0. Here's y component is put x equals to cosine t, and z component put x equals to cosine t, y equals to sine t. So let me scroll down. So then our vector field is 0, cosine t times sine t. Then take the dot product with r prime t. So this is 0 times minus sine t, 0, cosine t times cosine t, cosine square t, plus 0 times cosine t, sine t is 0. So we have cosine square t. So let's use this Stokes theorem to compute the surface integral. So the Stokes theorem right side is the surface integrals of curl of vector field f over the surfaces equals to, left side is simply the line integrals of vector field f over the closed curve C. This equals to, then we parameterize our curve. Now we are instead of computing surface integral on the right hand side of the Stokes theorem, we are computing the left side of the Stokes theorem, which is the line integrals. So I'm in this state, so put limit 0 to 2 pi for this integrals, and then this equals to, by definitions, f of rt dot r prime t dt. We computed here f of rt dot r prime t, which is cosine square t dt. Then 0 to 2 pi, we use the trigonometric identity here, cosine square t equals to 1 plus cosine 2t over 2 times dt. Then take the integration, so take 1/2 outside, this 1/2 outside, then integration of 1 with respect to dt is t, plus integration of cosine 2t with respect to dt is sine 2t over 2, put the limit t equals to 0 to 2 pi. Then 1/2 as it is, put t equals to 2 pi, sine 2 times 2 pi, 4 pi is 0, so simply 2 pi. And for the lower limit, when t is 0, this is 0, sine 0 is 0, so simply I have 1/2 times 2 pi, cancels 2, so pi. Great. Now let's move on. Let me scroll down. That's better. Example 2, evaluate the line integrals of vector field f over the simple closed curve C, where vector field is given as capital F equals to x plus y square. That's first component. Second component y plus z square. Third component z plus x square. And our curve is the triangle with the vertices 1, 0, 0, 0, 1, 0 and 0, 0, 1 oriented counterclockwise. Great. So now here, instead of computing line integrals, we are computing the surface integrals using Stokes theorem. Great. So first, what is our surface area? Our surface is this triangular region with these vertices 1, 0, 0, 0, 1, 0, 0, 0, 1. Then the equation of the surface is with intercept x-intercept 1, y-intercept 1, z-intercept 1 is x plus y plus z equals to 1. Then z equals to function of gxy equals to 1 minus x minus y. Take the partial derivatives. So gx minus 1, gy minus 1. Then our normal vector is this, by definitions, normal vector equals to negative gx, negative gy, 1, which is 1, negative gx is 1, negative gy is 1, and 1 is 1. Then we need to compute the chord of the vector field. So the chord of vector field f equals to, this is the 3×3 determinant with I, j, k, this is the nabla component, and this is the vector field component. Let me scroll down here. Yeah, and then expand this determinant, that gives you negative 2z, negative 2x, negative 2y. Now that's our p, q, r. And I need a limit of the Dahal integral. So let's project the surface on the xy plane. So simply put a z equals to 0. This gives x plus y equals to 1, which is this line. X plus y equals to 1 is this line. So this line and x-axis and the y-axis gives us the two-dimensional domain D, or region D. Then let's describe this domain as vertically simple. Draw the vertical slice, and the lower limit of y is given by x-axis, so which is y is 0, and upper value of y is given by y equals to, from this equation, 1 minus x, and for the x bounds, x equals to 0 to x equals to 1. Great. Now we are ready to evaluate the line integral. Excuse me. So let's start. That's better. Using Stokes theorem. So the Stokes theorem says on the left side is the line integrals of vector field f over a simple closed curve C equals to the double integrals of chord of vector field f over the surface S. S is the surface enclosed by the curve C. And this equals to double integrals. We missed the integrals here. The double integrals chord f dot n ds. Or let's go down here, which is double integrals over d of negative p times dx minus q times dy plus r outside dA. So that's the formula. Then our limits, we replace dA by dy dx, negative p times dx. Let me go up here. What is my negative p is now just 2z, and dx is 1, negative 1, dx is negative 1. So this negative times this negative is positive, but I have one more minus from the formula, so this gives me minus 2z, so this comes from there. Similarly, negative 2x, negative 2y, and dy dx, and in dy dx order, y integral is our inner integral, x integral is our outer integral. And now we are integrating with respect to dy and dx, so let's replace this z again in terms of x and y, which is given equations of the surface. So from here, z equals to 1 minus x minus y. Let me scroll down. Great. Then let's integrate. So first integrate with respect to y. Oh, before that, let's put this value z equals to 1 minus x minus y. Simplify, which is here. This gives us only just a negative 2. Then integrate, then pull negative 2 outside. Then we are integrating of integrand function 1 of 1. That means we are simply finding the area of this region, which is a triangular region. We can use a shortcut method. The area of the triangle is half base times height. So half, this is the base, this is the height. So then this is -2 as it is, half base height, cancel to -1. So we found the value of, in example 2, we find the value of the line integrals, but not computing line integrals as a line integral, but we computed line integral as a surface integral using Stokes theorem. Great. Let me go back to the example 1. In the example 1, we computed the line integral instead of surface integrals. Right here. Awesome. Now let's move on. Let's do example 3. That's better. Yep, that's better. So the example 3 says, evaluate the surface integrals of curl of vector field F over the surface S. Here we're talking about this part, yeah, where vector field is given as vector field capital F equals to xz, yz, xy, and the surface S is the part of the sphere of radius 2 that lies inside cylinder x square plus y square equals to 1 and above the xy plane and oriented upward. Great. So now here, we need to compute the surface integrals, but we are using a Stokes theorem and computing the line integrals. So to compute the line integrals, I need to parameterize the curve. So let's first find out what is our curve is. Let me start the solution. So for the boundary curve, solve the sphere and cylinder. Solve the spheres and then cylinder. That's the cross section there, right? Great. So what am I doing here? Oh, great. So then let's put x square plus y square equals to 1 on the equation of sphere. So this gives us 1 plus z square equals to 4. Subtract 1 both sides, so z square equals to 3. Then z equals to radical 3. Hence our space curve is c equals to x square plus y square equals to 1 at height z equals to radical 3. So circle at height radical 3. At height radical 3, we have a circle here. Awesome. Then in vector form, the equation of the curve is rt equals to xt, yt, zt. We can write x equals to cosine t, y equals to sine t, and z is radical 3, t between 0 and 2 pi. Take the derivative, r prime t equals to derivative of cosine t is negative sine t, derivative of cosine t is cosine t, derivative of radical 3 is tiny 0. Awesome. Then let's write our vector field in terms of t. So it is our vector field. Our vector field is x times z, y times z, x times y. Let me scroll down. So then here x times z. So what is our x? Our x is cosine t and z is radical 3. So radical 3 cosine t. Similarly, radical 3 sine t. Cosine t, sine t. Great. Then let's take a dot product of this vector field f with r prime t. I'm dotting here. Negative sine t times radical 3 times cosine t, this term, plus cosine t times radical 3 times sine t, and then the third term will just disappeared because 0 times cosine t sine t is 0. Plus minus cancelled, so we found the f dot r prime t is 0. Then by Stokes theorem, what we are computing here? We are computing the surface integrals, but using Stokes theorem we are computing line integrals. Awesome. Let's go down here. So the curl f, surface integral of curl f over s surface equals to the line integral of vector field f over c, but we found f dot r prime t, which is same as f dot dr. We found the dot product is 0, so then this equals to f of rt dot r prime t, which is 0. So the line integral of 0 is 0. So we found the surface integrals using Stokes theorems and computing here the line integrals. Great. So we finished these sections, and we finished the multivariable calculus 3 or calculus 3. Thank you.